AP Calculus BC, Unit 8, Day 10, office hours. This is the pretest for the test. So you're going to have on the first part, first page, you're going to have 5 questions like this, open or closed interval, or impossible repeating decimals. And you need to give its value. That means find the sum. So they got to be geometric series. If it diverges, you say it diverges. So this one, the A value is 1/3. The R value is 1/3. You need to show that you've checked whether the absolute value of the R is less than 1. That needs to be in your work. So the sum equals A over 1 minus R. So that's 1/3 over 1 minus 1/3. 1/3 over 2/3. 1/3 times 3/2. The answer is 1/2. That's the work you need to show. So the next one, A value is 4/5. R value is negative 1/2. Is the absolute value of R, is it less than 1/2? Yes, it converges, and you see that work. S equals A over 1 minus R. 4/5 over 1 minus negative 1/2. So it's 4/5 over 3/2. So it's 4/5 times 2/3. So it's 8/15. Okay, next one. What I would do is I'd rewrite this as 0.27, 0.0027. So this is 27 hundredths plus 27 tenths, hundredths, thousandths, 10 thousandths. It's 27 tenths, hundreds, thousands, 10 thousands, 100 thousands, millions. Okay, so you can't use the trick from Calc AB where we turned it into a fraction. I won't give you credit for that. I want you to treat it like a geometric series. That's what this test is about. So the A value is 27 100ths. The R value is 1 over 100. Make sure that you show me that you thought and confirmed that the R value was less than 1. So it converges. So S equals A over 1 minus R. A is 27 over 100. 1 minus R is 1 over 100. It's 27 over 100 over 99 over 100. So we get 27 over 99. Take it 9 out, 3/11ths. Next one. It could be useful to rewrite it in open form just to get the R value right and stuff, but that's up to you. This is probably the A value. This is if you plug n equals 1 in, that's going to give you your A value. So the first term is negative 2/3, not 2. Then you multiply by negative 1/3, you get positive 2/9, and negative 2/27. So the A value is negative 2/3. R value is negative 1/3. Absolute value of R has to be less than 1. It is, so it converges. So S equals A over 1 minus R, negative 2/3 over 1 minus negative 1/3. It's negative 2/3 over 4/3. Negative 2/3 times 3/4. Get negative 1/2. Sum can be negative. Okay, number 5, you see cosine, you start thinking of all that other stuff we do. Nope, this is cosine of pi over 4, which is just a number. It's root 2 over 2. And then I would simplify this further down. I do the squared and then in afterwards. So it gives you 2 over 4, which is 1/2. So this is the same thing as 1/2 to the n. So first term is 1/2, and that's going to be 1/4, and that's going to be 1/8. So the a value is 1/2. The r value is 1/2. The absolute value of r is less than 1, so it converges. So the sum equals a over 1 minus r equals 1/2 over 1 minus 1/2 equals 1/2 over 1/2 equals 1. So none of these diverged, but I can guarantee you that I'll probably give you at least one that diverges on the test. And that just simply comes from when the absolute value of r is not less than 1 for a geometric series. Okay, power series. So these are the series that you should probably have memorized, be able to, recreate. This one I have memorized because I think of this as the sum equals a over 1 minus r. So that's your a, and there's your r. R is positive x. So the first term says write the first 4 non-zero terms. So the first term is going to be 1, and then plus x squared plus x cubed. You should have pluses in between them. It's a series. They're being added up. Now we're going to write the closed notation either starting at 0 or 1. I could ask you either way, but it'll be shown there. So it helps if you want to write n equals 1, 2, 3. So it looks like it's always x to the n minus 1. Or you could do x to the n if you started at 0. So okay. So closed form, sigma notation. All right. It says a lower limit of 1, but some of these have 0, so you should be ready to go either way. This one, similarly, I don't memorize it. I just say, oh, that's a. R is negative x. Right, so the first term is going to be 1, then minus x plus x squared minus x cubed. So we definitely need a negative 1 component to the n value if we're starting at 0, and then x to the n. Otherwise, we could start at n equals 1 and be negative 1 to the n plus 1 or minus 1, and then x to the n minus 1. Okay. Next one. Now, this one, I remember this comes from the integral of 1 over 1 plus x dx, and that series is actually the one we just did. 1 minus x plus x squared minus x cubed. And, we could even write the nth term in here. It has a negative 1 to the n, x to the n. So if we integrate that, we get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So, or you could just recreate that. So this is going to be negative 1 to the n plus 1 if we're starting at 1, x to the n. If we were to start at 0, it'd be negative 1 to the n. Oh, I forgot something. X to the n over n. No factorial. Negative 1 to the n, x to the n plus 1 over n plus 1. Okay, inverse tangent. I'm like, oh, well, that comes from 1 over 1 plus x squared. So, in that series, starts at 1, and then negative x squared plus x to the 4th minus x to the 6th. So the antiderivative, if we integrate this, is going to be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. So first 4 non-zero terms. Now, if we start at n equals 1 here, n equals 2, n equals 3, it looks like it's double. It's x, there's a negative 1 to the n plus 1, and then it's x to the 2n minus 1, 2n minus 1, 2n minus 1 over 2n minus 1. Or if we were to start at 0, be negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So you're going to have some of those or some other series that are, closely related to the memorized ones. And we got a few more on the next page. Now, these ones I have are like in their most basic memorized form, but you got to be ready that I might give you something that's a little tweaked version of those. So here's a few more. Now, these ones I just memorized. I kind of memorize them all together. E to the x I memorize is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. If you really want to, you could recreate any of these from a Taylor polynomial. Okay, so that's n equals 1, n equals 2. So it looks like it's always x to the n minus 1, right? Over n minus 1 in parentheses factorial. Otherwise, we could start at 0, and it would be x to the n over n factorial. Now, sine is just the odd terms. Sine is an odd function. Cosine is an even function. They have odd symmetry, even symmetry. Odd polynomials usually end with the odd power, have an odd degree. So it's going to be the odd terms. X the first. And it's also alternating in sign, plus, minus, plus. So if we start at n equals 1, n equals 2, n equals 3, there's an alternating sign. So negative 1 to the n plus 1, x to the 2n minus 1 over 2n minus 1 factorial. Or if we started at 0, it'd be negative 1 to the n, x to the 2n plus 1. Okay, cosine is just the even terms, so it's 1 plus x squared over 2 factorial, actually minus plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. So it's going to be negative 1 to the n plus 1, and then x to the this one's 2n minus 2, 2n minus 2. Or if we started at 0, negative 1 to the n, x to the, put 0 here, 2n, it's the 2n, x to 2n, 2n factorial. Need parentheses around that factorial. So have those all memorized. We'll be able to create them quickly and effectively. All right. Now on the next part of the test, and this could also sort of be on that part of the test. Something like 14 could be on the second page of the first part. Then the next part, you could do Taylor polynomials given orders or degrees, which is the highest power of an exponent. They're truncated, they don't go on forever. So now we could build it, since this is centered at 0, I could just say, I'm going to do this as S equals A over 1 minus R and say, okay, well, that's A, R equals 2X. So, so the series is going to be X multiplied by negative 2X is minus 2X squared. Plus, oh wait, not negative. Okay, plus 2x squared, r is positive 2x, plus 4x cubed plus 8x to the fourth. So this is the fourth order Taylor polynomial. Alternatively, you can take lots of derivatives. You can say, okay, well, the 0th derivative is x over 1 minus 2x. And then the first derivative, you do questionable low d high minus high d low all over low squared. That's going to be 1 minus 2x plus 2x. So it's going to be 1 over 1 minus 2x squared, which I would just treat as an exponent, power problem. So the second derivative is going to be negative 2, but another negative 2 is going to pop out because of the chain rule. So it's positive 4 over 1 minus 2x cubed. And then the third derivative is going to be negative 12 with another 2. Negative is going to be positive 24 over 1 minus 2x to the fourth power. And then we need the fourth derivative. So it's going to be negative 96 192 over 1 minus 2x to the fifth power. Okay, then you'd plug 0 into these. And this one you would get 0. And this one you would get 1. And this one you would get 4. And this one you would get 24. And this one you would get 192. So then if you go to build it, so this is the OR option. Okay. P sub 4 equals first coefficient 0 times x minus 0 to the 0th power of a 0 factorial plus 1. We could probably just drop the x minus 0, just put x to the first over 1 factorial plus 4 x squared over 2 factorial plus 24 x cubed over 3 factorial plus 192 x to the fourth over 4 factorial. And if you simplify that, that would give you the same answer. So probably try and do those, memorize the Maclaurin series. So like this one right here, I just say, oh, well, e to the x, I have that memorized. That's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. And then if I want to multiply by x, then I just multiply this by x. And my fifth order Taylor polynomial is going to be x plus x squared plus x cubed over 2 factorial plus x to the fourth over 3 factorial plus x to the fifth over 5 over 4 factorial. And there you go. Quick and easy. Otherwise, you could do all the derivatives. You say, all right, well, the 0th term is x e to the x. And so then the first derivative, I'm going to have to do product rule x times e to the x plus e to the x times 1. And then the second derivative, you're going to do another product rule, your x times e to the x plus e to the x times 1 plus another e to the x. Now, there is a pattern here that maybe you could c. So it's x e to the x. I bet it's going to be 3e to the x because the last one was x e to the x plus 2e to the x. And the one before that was x e to the x plus 1e to the x. And the one before that was just x e to the x with 0e to the x. So fourth derivative is x e to the x plus 4e to the x. And the fifth derivative is x e to the x plus 5e to the x. So then we would have to plug 0 into these. And that's going to be 0. And that's going to be 1. And that's going to be 2. And that's going to be 3. And that's going to be 4. And that's going to be 5. So it's very doable. It just takes a lot of time. So then you could construct it and you say, okay, first term is 0 times, x minus 0 to the 0th power over 0 factorial plus 1 times x minus 0 to the first power over 1 factorial. We just drop the minus zeros. And then if you simplify this, you get the same thing we just got there. So, or that work, or all this work. Now, next one's centered at 2. So we don't have luck there. But the next one is nicely, all the derivatives are done and evaluated for us. We don't even know what the function is. So third order would be 5 times x minus 2 to the 0th power over 0 factorial plus 4 x minus 2 to the first power over 1 factorial plus 8 x minus 2 to the second power over 2 factorial plus 24 x minus 2 to the third power over 3 factorial. And then we could simplify it. Like the first term is just going to be a 5 and then plus 4 x minus 2. I wouldn't FOIL out the binomials. 8 divided by 2 is 4. 24 divided by 6 is 4. So that one we did the long way, except that a lot of that work was already given to us. Okay, next one. E to the x centered at x equals 3, fifth order. So I think we just got to do it the long way. So we have the 0th derivative is e to the x. This one's going to be easy, thankfully. Right? And so if you plug 3 into each of these, they all give you the same thing this time, e cubed. So the fifth order Taylor polynomial is going to be e to the third x minus the center to the 0th power over 0 factorial. Those are going to be 1s. Plus e to the third x minus 3 to the first power over 1 factorial. Plus e to the third x minus 3 squared over 2 factorial. Plus e to the third x minus 3 to the third power 3 factorial plus e to the third x minus 3 to the fourth power over 4 factorial plus e to the third x minus 3 to the fifth power over 5 factorial. Okay. So there you go. Okay, next page, have some more of these. So you're gonna have a bunch of these, like part 2 the test. But here's one that's centered at 0. So let's try and take advantage of that. Now this needs to be a 1 for that sum equals a over 1 minus r. So I want to rewrite this as if I divided 3 out of everything on the top and the bottom. Right? So then a equals 2, r equals negative 2/3 x. So the third order Taylor polynomial is going to be, it's centered at 0, right? So 2 minus 4/3 x plus 8/27 x squared minus 16 over 81 x cubed, and you're done. Or you can do a bunch of derivatives. Which, a lot more work. You start with the 0th derivative. I don't really want to do chain rule. Okay, so first derivative is -6, then you get -2, -12 over 3 plus 2x squared. The second derivative is positive 24 times another 2, 48. Next derivative is negative 120, negative 144 with another 2, 144, 288. And then you would plug the center in 0, which would give you 2, -4, 16, 96, -96. Or did I mess that up? Oh, wait. 3 to the 4th. So that's 9, 27, 81. 2 plus 8 is 10 plus 8. So 3, I could take a 3 out of this. I think I just came up with 96. 3 out of this would be 27. Then we take another 3 out, it'd be 32 over 9. So negative 32 over 9. So then you'd have to start writing it. Say, okay, 2 times x, 0 over 0 factorial, that's a 1, minus 4, x to the first over 1 factorial, plus 16, x squared over 2 factorial. Did I do that right? Oh. See, I was doing these numbers wrong. This isn't 12 over 3, it's 12 over 9, so it'd be 4/3. This isn't 48 over 3, it's 48 over 27, which we could reduce to 16 over 9. Okay. So this is going to be -4/3. This is going to be 16 over 9. And this is going to be minus 32 over 9 times x to the third over 3 factorial. And then you have to try and clean it up. So we would get 2 minus 4/3 x. And this is going to be 8 plus 8. I don't know if I messed something else up. Okay, let's see. Minus 4/3, 16 ninths. Which gives you 8 ninths. I think I made a mistake over here. Should be 9. Should be 27. Okay, that makes more sense now. So now you get 8 ninths x squared minus, this is going to be 6. Take a 2 out. 16 over 27. Or just do it the first way, which I made a little mistake on, but whatever. Okay, next one, centered at 0. You know, don't do this the hard way. I mean, x sine x is x times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then you're going to add cosine of 2x. Now, cosine of 2x is a cosine curve with 2's added into it. 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial. So we just want 4th order. So this is going to be x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial. 4th order means we just want those. This one is going to be 1 minus 4x squared over 2, so 2x squared, 16 over 24. 16 over 24 is going to be 2/3 x to the 4th, and you could keep going, but that's it. So now, if you add these together and put them in the same form, you get 1 minus x squared. It's going to be 6. 4/6 minus 1/6 is 1/2. Otherwise, you do a ton of derivatives. These ones would be really not fun. I don't even want to do it. You can look at my work if you want to see it. That's not fun. Now the next one's centered at 1, so we got to do it that way. So next one, yeah, the 0th derivative. The first derivative, it's a product rule. X times derivative that. It's natural log of x times that, so that's a 1. And then the second derivative, it's going to be 1 over x. And then the third derivative is going to be negative 1 over x squared. And the fourth derivative is going to be positive 2 over x cubed. So then we're going to plug 1 in. Natural log of 1 is 0. This has a 1 already, plus a natural log of 1, which is 0, but you get 1. Okay, so then the 4th order Taylor polynomial is going to be 0 times x minus 1 to the 0th over 0 factorial, so that just goes away. Plus 1, x minus 1 to the first power over 1 factorial, plus 1, x minus 1 squared over 2 factorial, plus negative 1, x minus 1 to the third power over 3 factorial, plus 2, x minus 1 to the fourth power over 4 factorial. So we could clean it up a little bit. X minus 1 plus x minus 1 squared over 2 minus x minus 1 cubed over 6 plus that's going to be 24. So it becomes 12. So we had to do it the long way that time, but it wasn't terrible. Now, on part 3 of the test, you're going to have to do like all these other random things. Interval of convergence for 13 and 17. So 13 had an R value of 2x, right? So the absolute value of R has to be less than 1. So that gives you negative 1 to 1. It gives you negative 1/2 to 1/2. And we usually write it in interval notation. Okay. 17 is above. It had an R value of negative 2/3. So the absolute value of R has to be less than 1. So it's going to be 2/3 x between negative 1 and 1. So it's going to be negative 3/2 x to 3/2. Interval of convergence. Okay, how about find the third derivative of 0 from this Taylor polynomial? Now here's the way to do it. Third derivative, we need the one with the third power. This term right here is constructed by the third derivative at 0 times x to the third power over 3 factorial, right? So let's set it equal to that and solve for this guy. So the x cubed's dropped out. Then you got to multiply both sides by 3 factorial. And f triple prime of 0 equals 60. That's how you do it. So you have something like that on part 3. Let f be a function series converges, and they're telling you that the nth derivative is always less than 2, no matter what. Centered at x equals 3, approximating 3.1, with an error of less than 0.001. So I'd like to use a calculator on this just to get the decimals, but this is Lagrange error bound. So L.E.B equals the n+1 derivative at some value c, x minus a to the n+1 power over n+1 factorial. Should be able to write that down from memory. So for us, we know it's going to be less than, because this is the worst case scenario. You can plug a 2 in for this. We're evaluating 3.1. The center is at 3. And n+1 over n+1 factorial. So this is getting a little more simplified. And so we can just start. It says minimum number of terms. So n equals 0 is 1 term. And so we can say, well, L.E.B is less than, if we plug 0 in here, it's going to be 2 times 0.1 over 1 factorial, which is just going to be 0.2. Is that less than 0.001? Nope. So then we'll just keep going. N equals 1, which corresponds to 2 terms. L.E.B is less than 2 times 0.1 to the first to the second power over 2 factorial. So you could use your calculator if you want. You could do 2 times 0.1 to the second power divided by 2 math PRB factorial. I'm not saying it wouldn't be faster. So, not surprisingly, the more terms you take, the smaller the error gets. Not small enough. Okay, we'll try 3 terms. Now, if you feel confident, you can skip some of these, but if you overshoot it, you better go back, work backwards until you get it just right. Okay, if I just took 10 terms, it'd probably be good, but I want the minimum number of terms. Now, here's the thing I'm going to do. I'm going to use my previous calculation, second enter, and just change that to a 3 and that to a 3. You get 3.333 times 10 to the negative fourth, which is 0.000333. Is that less than 0.001? Yes, it is. So we need 3 terms. N equals 2, 3 terms. I want a number of terms. So 3 terms. Okay, a few more. Approximation. Use when x is small. Estimate the maximal error when x is between 0, when the absolute value of x is less than 0.1. So we need, for Lagrange error bound, you need the next term, right? So we need the third derivative for sure. And this is centered at 0. This is a Maclaurin series. If you look at this, this is the Maclaurin series for e to the x. So a equals 0. So the 0th derivative is e to the x, e to the x, e to the x, e to the x. I know this one's simple, but I'm just showing you the work I would show if it was more complicated. So Lagrange error bound is the n plus 1 derivative at some value c, x minus a to the n plus 1 power over n plus 1 factorial. So for us, this is that third derivative. The function looks like this, and we're looking from -1 to 1. So usually we just plug a certain value in, but this is like a window. So we're looking for the worst value right there, which is here. You plug 1 in. No, not 1.1. You plug 0.1 in. So we know the worst value is going to be e to the 0.1. The value we're evaluating it at, we've got to think worst case scenario would be 0.1 minus 0. Because it's a whole interval of values, but worst case to the third power over 3 factorial. So this is 6, by the way, or you could do it all on your calculator. It's up to you. Okay. So if we do that, we can say second e to the 0.1 times 0.1 to the third divided by 3 math PRB factorial if you want. And we get 1.84195 times 10 to the negative fourth, scientific notation. Let's say that we only want 3 significant digits, 3 sig fig. So 3 decimal accuracy, this would be 0. This would be 0.000184. And I think we should always round up. Always round up, even though I may have different answer on my online version. You could write it in a scientific notation. This be the correct way to do that. Okay. Next one. Let f be a function whose seventh derivative, they're giving you the seventh derivative. If x equals 1 is in the interval of convergence for a power series, then the Taylor polynomial degree 6 centered at x equals 0, degree 6, will approximate f1 with an error not more than what? So this is Lagrange error bound. We need the n plus 1 derivative at some value c, worst case scenario, x minus a to the n plus 1 power over n plus 1 factorial, need parentheses. So for us, they've kind of done the hard part for us. They found the seventh derivative, which I would draw a sketch. I need some kind of evidence. You could do EVT full blown, or you could use a picture. Now, this is what that looks like. 10,000. This is 2 pi. Now, we're going to plug 1 in. So this is about 6, right? So this is about 3. This is about 1.5. So 1 is like somewhere around here. So we're looking just at this chunk of the graph right there. And the worst value is 10,000. Okay. 10,000. And we're evaluating at 1. The center's at 0. And this is to the 7th power over 7 factorial. So that's just going to be 10,000 over 7 factorial. My calculator. We get 1.984126. So let's say I asked you for 3 significant digits. You would tell me 1.99. All right. Or if we were doing 4, it'd be 1.985. Round up for sure. Round up for sure for error. Because it's supposed to be worst case scenario. If you round or truncate, if you round down or truncate, your worst case error is actually less than the real worst case error. So, okay, next one. For all x, here's a closed function. The derivative would equal what? So I think we could simply take the derivative of this term. Now, anything with numbers and n stays the same, -1 to the n plus 1. Now, the x right here, you can move the 2n plus 1 out front. Power rule, decrease it by 1. On the bottom, we have a 2n plus 1 factorial. We could reduce this because 2n plus 1 factorial is 2n plus 1 times 2n factorial. And so I think we could say, all right, n equals 0, -1 to the n plus 1, x to the 2n over 2n factorial. So do we see that answer here? There we go. Okay, last one on the graph below shows the function. Shows a function with a relative maximum at x equals 2, relative max at x equals 2, and a relative min at x equals 5. Okay. And the approximation of f of x near x equals 5 for a second degree Taylor polynomial centered about x equals 5 is given by this. So this is your second degree Taylor polynomial. Second degree Taylor polynomial. Okay. Which of the following is true about A, B, and C? Okay. Well, these A, B, and C values partly come from this is the 0th derivative at the center, and then x minus 5 to the 0th power over 0 factorial, plus the first derivative at the center, x minus 5 to the first power over 1 factorial, plus the second derivative at 5x minus 5 squared over 2 factorial. So these values, A is this, B is this, C is that. Now, first off, the slope at 5 is, the value at 5 is like negative 5. But that term, yeah. And then that's what A is, right? That's A. And then the first derivative at 5 over 1 factorial is going to give you B. First derivative at 5 is 0. And so that's going to give you the B value. And then the second derivative at 5 over 2 factorial, second derivative of 5 is positive. So that's your C value. So A is negative, B is 0, C is, so A is negative, C is positive, and B equals 0. So if we were to put these all in order, A is negative, A is negative, A is negative, B is equal to 0, and C is positive. So I think it's got to be A. It's kind of a interesting problem, combining your knowledge. That's it. Be ready for the test, all parts.